Private notes, a live webcam, and a microphone are exactly the inputs I do not want bouncing through somebody else's server. This is fluid coding and AI, and today LiteRT.js gets a browser runtime engineering test, not a local model victory lap. The real question is whether faster local inference survives the download, memory, compatibility, conversion, and privacy bill. Google launched LiteRT.js as a JavaScript binding around its LiteRT stack. CPU runs through XNN pack on WebAssembly. GPU runs through WebGPU, and WebNN is the experimental path toward system accelerators. On one M4 MacBook Pro, Google's chart reports up to 3.33 times the throughput of ONNX Runtime Web on CPU and up to 3.15 times on WebGPU. Promising? Absolutely. Universal? No. The article does not publish raw runs, variants, browser build, model hashes, memory, power, or time to first result. The test app is Private Workspace Check. It has 3 jobs. First, paste private notes, build embeddings locally, and search them by meaning. Second, sample the webcam for a small desk or room classification. Third, hold a button, capture one short audio clip, and run a tiny voice or sound task. This is intentionally awkward. Text, pixels, and audio exercise different pre-processing and operator paths. While the product promise stays coherent, useful private inputs should remain inside the browser. It also prevents this from becoming another demo where one image classifier runs 50 times and declares the web solved. The first invoice arrives before useful inference. The browser needs JavaScript, one selected WebAssembly runtime, model files, tokenizers or labels, compilation, allocation, and warm-up. The LiteRT package inspected for this research had an 11.4 megabyte compressed tarball before any model. Google's acknowledged embedding demo uses an embedding Gemma model around 183 megabytes. That may be reasonable after explicit consent and caching. It is not a polite surprise on page load. So the stopwatch starts at navigation, and the test records transferred bytes, compile time, first real result, warm reload. Then the result that matters is not the fastest one. It is whether run 2 is still correct. A current GitHub issue reports that a YOLO model on one Adreno 830 device produced a correct first WebGPU inference, then non-deterministic bad outputs on later runs. That is a detailed user report, not proof of a universal LiteRT bug. But it changes the test. Every accelerator result must be compared with a CPU reference across hundreds of repeats while logging the requested backend, the backend actually selected, and whether the graph was fully accelerated. A fair runtime comparison needs the same source weights, input tensors, pre-processing, output checks, and task goal. Compare LiteRT WebAssembly with ONNX Runtime WebAssembly, then compare their WebGPU paths where both genuinely work. If formats require different weights, quantization, or pre-processing, call it a task-level comparison, not a runtime speedup. Measure at least 50 warm runs, with median and 95th percentile latency, plus end-to-end time from input ready to useful result. Until those raw measurements exist, there is no honest independent winner here. The only numbers available are Google's scoped, provide. WebAssembly is the compatibility baseline. It uses XNN pack on the CPU and should remain the path that keeps the app useful when acceleration is unavailable. WebGPU is the practical performance enhancement today, but browser version alone does not guarantee a usable adapter, driver policy, or operator path. WebNN is more future-facing. Google's own guide requires experimental browser configuration, and the W3C specification is still a work in progress. So WebNN results belong in a clearly labeled appendix. They should never be blended into a default browser average or presented as normal NPU. The model format is not a free portability spell. The PyTorch path requires export-compatible graphs, static input and output dimensions, and no Python control flow driven by runtime tensor values. LiteRT supports TensorFlow and JAX paths too, but operator coverage, data types, layouts, quantization accuracy, and accelerator delegation still have to be tested. The docs also describe shape mismatch, limited aligned input and output types, unsupported operations, and WebAssembly memory limits. A converter can finish successfully while the product still fails. Model conversion. Some memory is where browser convenience meets native runtime reality. LiteRT tensors expose explicit delete calls, and compiled models and runtime objects also need lifecycle management. Add TensorFlow.js preprocessing, and there is another set of tensors to tidy or dispose. The stress test should run webcam inference for 5 to 10 minutes, switch among tasks, track the signals the browser exposes, then delete tensors and models and stop every media track. A pass means memory reaches a plateau and materially returns toward baseline. A rising line, device loss, or tab crash. Local inference can improve privacy, but the runtime name does not prove it. A page can run every model locally and still send notes through analytics, third-party scripts, or an ordinary network request. The privacy test self-hosts the app, runtime, models, tokenizer, and labels. After loading, the network log must show 0 outgoing requests containing text, embeddings, frames, audio, or predictions. Then the cached app has to work offline. Camera and microphone access stay opt-in, tracks stop immediately after use, and local data can be cleared. ONNX Runtime Web can support the same local architecture. Privacy is an audited system. The webcam does not need pretend cinema speed inference. Sampling 5 to 10 frames per second may already feel immediate for a desk check while reducing heat and cue pressure. The audio task should also start small, 1 user-triggered clip and 1 classification. A current issue report describes difficulty using a packaged non-module WebAssembly glue file inside an audio worklet. That report is not a universal platform limit, but it is a good reason to test the simple path before promising real-time audio processing. 1 model at a time is also the sensible default, unless concurrent use is a real product requirement. There is a real case for LiteRT.js. Google is bringing a mature on-device runtime family, XNN pack, conversion tooling, quantization work, and shared.tf Lite artifacts into the browser. Its launch chart shows LiteRT ahead of ONNX Runtime Web on all 10 model and backend points presented, although several gains are modest and the methodology is incomplete. Teams already shipping LiteRT models elsewhere may gain more from artifact reuse than from a benchmark trophy. And the model tester is a useful first gate for backend execution. Just remember that random input success proves ground. My evidence-based verdict is conditional. LiteRT.js is a credible candidate for compatible static shape models when warm local latency matters and the download can be justified. It is not yet evidence for an automatic migration, a universal 3x win, or effortless NPU access. I would ship only with an explicit model download, progress and cancel controls, a tested WebAssembly fallback, backend and full acceleration telemetry, golden output checks, repeated run tests, disciplined cleanup, and a real privacy audit. WebGPU can be the upgrade. WebNN stays in the lab. If conversion, the remaining job is real hardware. Run current Chrome, Edge, Safari, and Firefox where available. Include Apple Silicon and a Windows Intel or AMD system, and add Adreno and Mali mobile devices if the conclusion claims mobile support. Publish cold start bytes, first useful result, warm median and 95th percentile, sustained memory, correctness, fallbacks, and failures. Without that matrix, the honest claim is narrow, Google's launch evidence is promising, and the engineering design is ready, but cross-browser performance is still unproven. That boundary is not disappointing. It is what keeps a runtime test from becoming marketing with a stopwatch. If this helped you separate local AI promises from browser engineering reality, like the video and subscribe to Fluid Coding and AI for more practical tests.